Hello, everyone. Welcome back. We are going to talk finally about elliptic curves in all seriousness. Last time we stated the Riemann-Roch theorem, and the Riemann-Roch theorem is a theorem that says something about these spaces of functions with some prescribed orders of zeros and poles, or orders of zeros, prescribed orders of zeros, and prescribed how bad some poles can be. And it gives you the dimension of those spaces, and it gives you some formulas about them. So in particular, this corollary is very important, and in particular, this formula for the dimension of a space, in particular when G is 1, which is the case we're the most interested in, when G is 1, that says that the space of the LD space, the dimension is equal to the degree of the divisor you're calculating a space of. And that allowed us to prove this corollary last time, that it says that if you have a smooth curve of genus 1 over k, so a projective dimension 1 variety that is smooth, genus 1, and it has at least 1 point over k, then there is actually an isomorphism that puts it in what we call a Weierstrass equation. Okay, so those are called Weierstrass forms. Weierstrass model. And so every elliptic curve can be given one such model. Okay, and that's very good. So and then we also, at the very end of class last time, we stated the Horowitz theorem, the Riemann-Horowitz formula, which is used to compute genera of other curves. So typically, you know the genus of one of the two of the curves, and then you use the formula to compute the genus of the other one. Typically, you know the genus of the one below, and then you compute the genus of the one above. Okay, so let's continue. Let me just give you one example of these type of transformation. So this elliptic curve is important in that, for example, if you want to know what numbers are the sums of two cubes, a very classical problem is what integers are the sum of two squares, of two perfect squares, and that we know the complete solution. But to characterize what integers are the sums of two cubes, that is not known in general, and you would have to be able to determine which ones of these elliptic curves have rational points other than a point at infinity. There is a point at infinity. In projective coordinates, this curve is x cubed, y cubed equals dz cubed. And we have, for example, a point O here, which is 1 minus 1, 0, right? So there is a rational point on that curve. It is a curve of it is smooth, it is projective, it is dimension 1, and you can prove that the genus is 1. What we're actually going to do is put it in Weierstrass form. So I'm going to do that for you. I'm not going to say exactly how to do it, but I'm going to give you a couple of references on how to do this in general. So it turns out there is a way to put this in Weierstrass form. It is of genus 1, and there is a map from E to some E hat given by, let me put it in also in projective coordinates, this one. So E, the map is defined that sends x, y, z to the point 12 dz, 36 dx minus y, x plus y. Okay, and it in fact it has the inverse can be written as x, y, z goes to 36 dz plus y, 72d, 36 dz minus y over 72d, and x over 12d. Okay, so that those maps give you this isomorphism from one place to another. You can actually just show the map in over in affine coordinates. I can tell you what that looks like. So this maps to, so the curve given by that in affine maps to this elliptic curve in short Weierstrass form, in fact. So this goes from xy maps to 12d x plus y, comma 36d x minus y, x plus y, and there's an inverse. I'm not going to write it. Okay, so you have a way to go from a cubic curve that is not in Weierstrass form to Weierstrass form, and you can work on the Weierstrass form and then come back and find points on either one. The way you change variables, that I'm not going to explain here in this class how you do that, but if you want to see it done, so how do you go from generic smooth cubic to Weierstrass form? This is actually explained, for example, in Silverman-Tate, in the undergraduate introduction by Silverman and Tate to elliptic curves. There, early on, they do an example of this. It's a little bit schematic. Then I actually wrote it in quite a bit more detail in my book, Number Theory and Geometry. So if you look in my book on number theory and geometry in section 15.3, I did in quite a bit of detail. The point of how you transform into a Weierstrass equation is the following. The point is that if you have one special characteristic of Weierstrass equations is that at infinity, so if you continue this and you find the point at infinity, the tangent line at infinity, maybe I should draw it in some other way. So the tangent line at infinity, so if this is the point O, it turns out that the tangent line at infinity is the line z equals 0, and it has a triple point of intersection at that point O. That is more than you ask for on a tangent line, right? On a tangent line, it has to have a double point of intersection, but it turns out it's a triple point of intersection. We call that an inflection point. And so at that point, that's where that characteristic of this form makes it be into a Weierstrass form. So here there is a triple point of intersection with the tangent line. So the way you change variables so that you go into a Weierstrass form is by, you have a point O, and then you want to change variables so that in the new variables, the tangent line at O has a triple point of intersection at O. Okay, so I'm not going to say how you do that in general, but it's a matter of you play with some lines and some change of variables so to make this happen, and that is how you find a model. So there is a strategy to this. This is not just some like magical change of variables that I found by working very hard and looking at it for hours. there is a method to do this, and it can be explained, but not here. Okay, so without further ado, we actually go on.
Sorry, Alvaro,
Yes.
can I ask a quick question about what we just covered?
Yeah.
Sorry if we went over this extensively last time and I'm just spacing on the concept, but can you remind us in what way the two curves that you just discussed are related? How would we articulate the way that the map psi is relating E and E hat?
So what it is giving you is such a thing. So the map, it is the same. So these are two curves that are isomorphic, meaning that you have a morphism to go from one to the other. So what you can think of it is that they are the same curve, but depending on what variables you choose for your curve, you're going to get different models for the curve. If you think of it in terms of function fields, the function field is the same function field, but the generators of the function field in the Weierstrass model are x and y related by this model, right? So if you look at this other, so in this equation, the function field is generated by x and y that satisfy that relation. What I'm saying is that there are two other functions, call them u and v if you want, that also generate the function field, but they have some other model that is in Weierstrass model. Okay, so that's why I actually use the word model for it, because in my view, there is a curve, but curves in projective space, essentially, they all, what you see is what sort of equation you pick for it. So you have a way to represent it in projective space, but depending on what generator you choose for the function field, that representation is going to look slightly different. But as long as there is a morphism going one way and the other way, then these two models are giving you exactly the same curve. They have exactly the same rational points, which is what we care about.
Mm-hmm. Okay, awesome. Thank you so much. Yes,
yeah,
it does.
Yeah, great question. Thank you. All right, so we're going to start now going a little bit more systematically through chapter 3. I jumped ahead after we saw Riemann rock to prove that there are Weierstrass models, but now let's go a little bit more in detail into chapter 3. So the first thing is to write the definition of an elliptic curve. So an elliptic curve, we still have the same standard for our notation that K here is a perfect field. But again, you don't lose much by thinking that K is either Q or a finite field FP. An elliptic curve. That E over K, this means that is defined over K. Is a smooth curve, so a projective variety of dimension 1 of genus 1 together with a point O that is in EK. So EK is the set of points on E that are defined over K. Okay, as opposed to EK bar, which would be the points on E defined over the algebraic closure of K. Okay, and what we've seen previously is that elliptic curves have Weierstrass models. So E over K can be written in a Weierstrass model. Okay, so there is by can be written, I mean there is an isomorphism to whatever E, in whatever format your curve E is given, there is an isomorphism to a model of this form, y squared plus a1xy plus a3y equals x cubed plus a2x squared plus a4x plus a6 for some ai in k. With some condition, so it can be given like this, but to have one of these models be an elliptic curve, we have to have a condition that makes it a smooth curve. So one can simplify this model. You can simplify the model in several ways. So this is called sometimes a long Weierstrass model. And you can typically bring them to a short Weierstrass model. So first of all, if your characteristic, the characteristic of the field is not 2, so for example, if you're not in F2, if you're not in function fields over F2, then you can do the following. You can replace the variable y by a new variable. So change y by a half minus a1x minus a3. And the effect this gives is that in the new variables, the new equation is y squared equals. So this change of variable gets rid of the linear terms in y. That's the point of it. So what I get is for x cubed plus b2x squared plus 2b for x plus b6. So this is some relic of some of notation that is just like classic notation. But in any case, it gives you some model of this form for some bi's in K. And you can find in the book, in Silverman's book, formulas for the bi's in terms of the ai's. Okay. We are going to give a name. So delta is going to be the discriminant of this polynomial. Because the discriminant of the polynomial, a discriminant is a product of differences of roots. So the discriminant is 0 even only if there is a repeated root, and that's going to tell us something about when this equation is smooth or not smooth. The only possible non-smooth points are going to be at the points where there is a double root, we will see. Okay. Right. So so I can remove the linear terms in y, and then oh, by the way, you see what y, the characteristic cannot be 2 because I need to divide by 2. Okay, so that is why the characteristic cannot be 2 in that case. Okay, so we can farther, we're going to be able to farther simplify the model. You see that we have here, we have a term in x squared there. We are able to get rid of that term by doing another change of variables. So, but now we're going to need the characteristic of the field to not be 2 or 3. If so, then I can change x and y by So if you change x by x minus 3b2 over 36 and y by y over 108, okay, then this gives you a model of the form y squared equals x cubed minus 27 c4x minus 54 c6 for some c4 and c6 quantities in K. Okay, and so this is an equation of the form y squared equals x cubed plus ax plus b, and this we call short Weierstrass model. But you see that I need the characteristic to be 2 or 3, not 2 or 3, to be able to bring it to this format every time. So when the characteristic is 2 or 3, we might need the full long Weierstrass form to work on it. Now, there are other change of variables. So remember that also one consequence of the Riemann-Roch theorem was that if we have a change of variables that preserves a Weierstrass form, a long Weierstrass form, then it was linear in x and y, right? Then that will also preserve a short Weierstrass form. If I do a linear change of variables in a short Weierstrass form, it will bring it back to a long Weierstrass form in general. So the changes of variables that preserve short Weierstrass forms, those have to be linear because of the Riemann-Roch theorem result of one of the 3 corollaries we proved last time. But they actually also have to preserve the short Weierstrass form. Then they have to be linear with no constant terms. So they have to be of the form replace x by u squared x prime and replace y by u cubed y prime. If so, such a change of variables brings your equation to an equation y prime squared equals x x prime cubed plus a over u to the 4 x prime plus b over u to the 6. Okay, so what this says is that we can give a unique model, for example, over Q. So if you have an elliptic curve over Q, we can give a unique model by these changes of variables. I can cancel denominators. I can just multiply by some appropriate u so that I clear denominators. So the a and the b can be integers. And there is no common 4th power and 6th power that divides both. Okay, and no integer u such that u to the 4 divides a and u to the 6 divides b. Okay, so I can always bring it to that sort of like, I don't want to say minimal model because that has another meaning in this that we will talk about, but that sort of minimality of the coefficients I can reduce until I get there. All right. In this model, in short Weierstrass, remember I defined delta to be the discriminant of that polynomial in x. I defined delta here. In these new variables a and b, the formula for delta, the discriminant, is given by minus 16 4a cubed plus 27b squared. Okay. If you actually compute the discriminant of x cubed plus ax plus b, that is 4a cubed plus 27b squared. But the 16, that 16 in front, it actually comes from the fact that there was a 4 in front of the x cubed in that original model with the b's, with the b coefficients. Okay. And we also define another quantity, j, which is called the j-invariant. And the j-invariant is defined by minus 1728 times 4a cubed divided by the discriminant. That's a strange way to write a quantity, but that is because the 1728 has a special meaning in all of this. So actually, C4, this C4 over here, this C4 has a formula also that is minus 48a, and then this is actually C4 cubed divided by delta. So that's perhaps a better way to write the j-invariant. So these are two very important quantities. The discriminant and the j-invariant are very important for elliptic curves in general. Now, it turns out, so how do they change? When we do these changes of variables, when you do one of these changes of variables, how do the discriminant and the j change? It turns out that in the new model, so if this was E and this is E prime, then the relationship is that the new delta changes by a 12th power of u. Okay. It turns out that j prime, the j prime equals j, therefore the name, you see the j is called the j-invariant, so something has to be invariant, and the invariance is that it doesn't matter what change of variables you do, the j will stay the same. No matter if you even change it back to some long Weierstrass equation, short Weierstrass equation, the j-invariant is the same j on all models, and all Weierstrass models of an elliptic curve, which is very useful. And you'll see why in a moment. In C4 prime, C4 changes by a 4th power. Okay. If you do one of these changes on a long Weierstrass equation, then you see, so it changes y squared plus a1 xy plus x cubed plus a2 x squared dot dot dot. It brings it to something of the form y squared equals, oops. If you do one of those changes, then so it turns out that it changes every AI coefficient by u to the power of the subindex of the AI. So remember when I skipped A5? So it turns out that this goes to, say, A4 divided by u to the 4x plus A6 divided by u to the 6. Okay, so it actually, those subindices help you remember what is the change, what does the change of variable do. There's other ways and other explanations of why these numbers are labeled and the way they are labeled, but that is one way to explain the numbering. Okay, so all of these formulas are in Silverman, so you can always refer to Silverman's book to find find all those formulas again if you need to. All right, so now here, this is proposition 1.4. So let E be given, so an elliptic curve that is given by a Weierstrass equation. Then A, there are three parts to this. It is non-singular. Let E be, actually, we are talking about a curve. So be a curve first, given by a Weierstrass equation. So we want to know when Weierstrass equations are smooth, for example. So it is non-singular if and only if the discriminant is non-zero. 2, we say it has a node if and only if the discriminant is 0, but C4 is non-zero. That means that a node, the singularities, you can classify what kind of singularities you get in a cubic, and what the singularity is going to look is something like this. There is going to be a crossing on your curve. And, oops, too thick. And it has a cusp, which looks like this, a singularity of that type, if and only if delta is 0 and C4 also vanishes. Okay. Then, so this proposition explains the usefulness of these quantities, delta, C4, and J. The explanation for the J is that two elliptic curves are isomorphic. And this is isomorphic over the algebraic closure, not necessarily over just K. So the isomorphism might be a little bit above of the field of definition of both, if and only if they have the same j-invariant. And finally, it turns out that for any j, any number in K bar, there is an elliptic curve with that j-invariant. So let J naught be a number in K bar, including 0. Then there exists an elliptic curve defined over K adjoint J0 with J invariant equal to J naught. Okay, so let me give some indication of how you prove these things. For part A, delta, remember, is the discriminant of the equation written in form y squared equals f of x. I'm going to assume in this proof, at least in the proof, I'm going to assume that the characteristic is not 2 or 3 for simplicity. Okay, so I can bring my model to an equation y squared equals f of x. Now, E is singular. When is E going to be singular? Such an equation is singular precisely when f of x has at least a double root. If you remember how we defined singularity, you would put it in projective coordinates, and then look at the derivatives of your equation. The equation, say, f of x minus y squared equals 0. Take the derivative of that with respect to x, with respect to y, with respect to z. When you take the derivative with respect to x, what you get is f prime of x. Essentially, you get f prime of x equals 0, right? So you have a point that you're trying to check if it's singular. So you have essentially, so you have a point that has to satisfy the equation, and it has to satisfy the derivative of f with respect to x is 0. The derivative with respect to y is 0. The derivative with respect to z is 0. So it turns out that if you work through this, and it's a good exercise for you to actually complete this proof in detail, this will tell you that the y is going to be 0, and this will tell you that f of x has a double root. So the fact that f of x is 0 and f of prime is 0, these two things together, it would tell you that f of x has a double root. Okay, but the discriminant will tell you when f of x has a double root. So this is 0 if and only if f of x has a double root, at least a double root. It could be triple, even only if the model is singular. Okay, so this gives you that delta tells you when there are singularities. So as long as delta is non-zero, you don't have singularities. Great. In addition, now for 2 and 3, so this gives you 1. For 2 and 3, notice that if I bring it all the way to short Weierstrass form, which I'm assuming that the characteristic is not 2 or 3, so I can do that. So if I have it in this form, then remember that C4 is 0 if A is 0. C4, where is it? It's right here. C4 is minus 48A in that model. So C4 is 0 if and only if A is 0. And if you have that Z4 is 0, which means A is 0 and delta is 0, where delta is minus 16, 4A cubed plus 27B squared, then Z4 and A delta equals 0, that tells you that A is 0 and B is 0. But if A is 0 and B is 0, the equation that you have is being reduced to something like this, which is a cusp, which the equation of that is a cusp. Okay, so this tells you that if delta is 0, then C4 is 0 if and only if you get a cusp. If C4 is non-zero, then this is not a cusp. There's a double point. So if C4 is non-zero, but delta is 0, then what happens is that you get something like you do get a crossing. Okay, so this would be a cusp, and this would be a node. All right, so let's move on to part 2. We're going to prove that two curves are isomorphic if they have the same j-invariant. So yeah, so first of all, suppose you have E and E prime, two elliptic curves defined over K. And let's suppose that that first of all, they're isomorphic. If E and E prime are isomorphic, then there is an isomorphism that brings, we can put them both in Weierstrass models. And if they are isomorphic, then the isomorphism is one of the changes of variables we have discussed before, is one of those linear changes of variables, because we proved using Riemann-Roch that they have to be one of those linear. So this is a linear change of variables, and these leave and these leave the j-invariant invariant, leave j unchanged, i.e. j equals j prime after one of those changes of variables. So the j's would be the same. Now let's go in the other direction. If the j of E equals the j of E prime, then what happens? If the characteristic of our field is not 2 or 3, then I can write both of them in short Weierstrass forms. So we have E is given by y squared equals x cubed plus ax plus b. And E prime is given by y squared equals x cubed plus a prime x plus b prime. And I have formulas for the j-invariants. So I have a formula for the j-invariant of E would be, actually, let me just simplify. There was a factor of 1728. So if the j-invariants are the same, what that's going to say is that the 4a cubed over 4a cubed plus 27b squared, I think I can actually just get rid of this 4, that a cubed equals a prime cube over 4a cube prime plus 27b prime squared. Again, in the j-invariant formula, that is a 1728 times 4 cubed times a cube in the numerator, but those two in the inequality of j would cancel out, and you get this equation. Okay, and if you unravel this equation, if you cross multiply, then what do you get? You see that the a cubed times 27 b prime squared. Oh, I see. I think actually I need the no, I don't need it. Yeah. So the a cubed times 4a prime cubed and the a prime cubed times 4a cubed, those will cancel out, and what you end up getting is that a cubed b prime squared equals a prime cube b squared. Okay, so you get this equality, and now we're going to argue case by case. So now case 1, if a is 0, then j is 0, then b cannot be 0 because E is non-singular. E is an elliptic curve. because the discriminant is non-zero. Okay, otherwise, if A is 0 and B is 0, we're dead, and it's singular. So we have A is 0, B is non-zero, and then from the equation, from this magic equation right here, A is 0, B is non-zero, so A prime has to be 0. Okay, the left-hand side is 0, B is non-zero, so A prime needs to be 0 forcefully, in which case J prime is also 0, and we can change actually the one change of variables that will bring you from one equation to the other is a short, so change with U equals B prime, a sixth root of B over B prime. Okay, so what I'm doing is that one change of variables x, y goes to y square x prime, u cubed y prime. And then if you do that change, because A is 0 and A prime is 0, it will change one into the other form, and it gives you the isomorphism we're looking for between the two elliptic curves. Okay, so that is the case where J is 0, then J prime is 0, and I can change variables from one to the other. Case 1, done. How about case 2? Case 2 is going to be the case that B is 0. So if B is 0, then what happens is that the j-invariant is 1728. If you compute the formula for the j-invariant, and if B is 0, then A cannot be 0, because again, the discriminant. And this tells me, the equation in green tells me now that B is 0, so the right-hand side is 0, A is non-zero, so B prime has to be 0 as well. And then I can do one of the short changes of variables with U equals A over A prime to the 4th power. That will actually bring you from one model to the other. Okay. Remember that these short change of variables would change y squared equals x cubed ax plus b. It would change it to y squared equals x cubed plus a over u to the 4th x plus b over u to the 6th. So when you change like this, then it will replace a by a prime, and you get an isomorphism of the two elliptic curves. Okay. So maybe I'll write that here. Recall that y squared equals x cubed plus ax plus b changes via that change of variables. It changes to y squared equals x cubed plus a over u to the 4th x plus b over u to the 6th. And then you can see why I want to take a 6th root of b over b prime to change b by b prime when a is 0, why I want to change a by a prime. I have to do a u that is a 4th root of a over a prime to do that. And you see that the isomorphisms are not necessarily defined over Q or over the base field. They might be in K hat, in K bar in the algebraic closure. These 4th roots are not necessarily in the base field. Okay, but that we didn't say they have to be. We said that they are isomorphic over K bar. All right, so now the last case is when A times B is non-zero. If A times B is non-zero, then I can actually, then you see that what happens is that the equation in green tells me that A over A prime cubed equals B over B prime squared. So there is a common factor u here, which is that if I take a common root, which is going to be, so a fourth root of this, that is the same that if I take a sixth root of this, right? Because so basically, what are we doing? Take 12 roots of both sides, then you're going to get that you have that the fourth root of a over a prime equals the sixth root of b over b prime. So it's the same number. And that's exactly what we need. If you take that u, that will give you an isomorphism between E and E prime. Okay. And that's that proves the part B. Right? So you'll see that the j-invariant being equal and the fact that we can reduce everything to short diastole models, it makes this computation easier to check that you have your means to find those isomorphisms. The last part of this proposition, let's go back to the statement, is my favorite. So this, the fact that for every number in K bar, there is an elliptic curve with that j-invariant. So let's prove that. So I want to find, given number j naught, I want to find an elliptic curve with that j-invariant. And the beauty of this is that I don't have to do an existence proof. I can give you an explicit proof, which is an explicit elliptic curve that if you compute the j-invariant, that is the j-invariant. So here it is. So if j is not 0 or 1728, then take E to be the elliptic curve given by the model y squared equals, or y squared plus xy equals x cubed minus 36 j naught minus 1728x minus 1 over j naught minus 1728. This model has a discriminant. I can compute it for you. The discriminant is j squared over j naught minus 1728 cube, and then you see that as long as j is j is not 0 or 1728, then the discriminant is non-zero and not infinity, right? If j was 1728, then there would be a 0 in the denominator of that delta function, and it would blow up. But luckily, we've chosen j to not be 0, 1728, so the discriminant is non-zero. So this is a smooth curve given by a Weierstrass model, so it is an elliptic curve. And you can compute that the j is the number I wanted. Okay? This is very important. This is this form. It actually comes up a lot in applications, in research, that the fact that you can construct elliptic curves with those j-invariants is very, very useful. Okay, in many situations. I've used this in research papers quite a bit. We left out two cases, j equals 0 and j 1728. So I just have to give you elliptic curves with those j-invariants. So if j is 0, we can take, for example, y squared plus y equals x cubed is a very nice elliptic curve. And the discriminant is minus 27, so at least if the characteristic is not 3, then you have an elliptic curve with that j. And if j is 1728, then you can take y squared equals x cubed plus x, which has discriminant minus 64. The j here is 0, the j here is 1728. Okay, so those are the two models with J0 and J1728. So that's it for the proof of that proposition. Let me just give you an example, and then I'm going to take a mini break, which is that I can use this formula, the formula in green, to compute elliptic curves with different j-invariants, and you can do that. So I have, for example, we just saw J0, y squared plus y equals x cubed has that j-invariant. You can go one by one. How about j equals 1? So if you put j equals 1, you're going to have denominators, but then I can do my changes of variables to clear the denominators and then reduce the coefficients. So you can play your game of the change of variables we've learned to simplify models. So for example, this is an elliptic curve with j equals 1. And you see that, oops, that even though j is 1, the model itself is not very simple. And this is the simplest model I could find with a j equals 1. Okay. How about j equals 2? So for j equals 2, I found that the simplest I could find was of this form. Okay, so the coefficients are starting to get a little bit big. It turns out that the j-invariant itself is not a good measure of is there going to be a very easy model for my elliptic curve. That is not what you're looking for. If you're trying to find models of elliptic curve with the small coefficients, the j-invariant is not your friend. For example, here is the elliptic curve that has the simplest coefficients actually has j-invariant that is 2 to the 12 divided by 11 of all things. This has a model y squared plus y equals x cubed minus x squared. If you really want to find elliptic curves with the small coefficients, what you're looking for is actually the conductor of an elliptic curve. Okay, so maybe it's a good time to also bring up the LMFDB. So at lmfdb.org, you have a database of elliptic curves at your disposal to find elliptic curves with certain properties that you may want. So if I look for elliptic curves, here is an elliptic curve, let's say, with j-invariant 2. It's not even in the database because the coefficients are already too large for the database. There is a lot of elliptic curves in the database, but not as many as you would think. It's actually very difficult to compute a database that is thorough, that it has all the elliptic curves up to a certain bound with all the, if you put some sort of bound on it in terms of the conductor, you want to find all the elliptic curves with such conditions, and these conditions are sometimes hard to verify. Okay, so let's remove that and talk about elliptic curves. Just let's see what happens if we organize them by what we call the conductor. That we will define much later in the class. So by conductor, the first elliptic curves that come up are the conductor 11 curves, and this is the 11A3 is the elliptic curve that I mentioned as an example of an elliptic curve with the small coefficients. And then you have other elliptic curves. So for example, 14A5 also has pretty small coefficients and so on. Okay, the database gives you all sorts of information about the elliptic curves. You have the elliptic curve, you have the conductor, you have the discriminant, which now we have defined the j-invariant, and other things we have not talked about yet, but you have quite a bit of information there about your elliptic curves and a way to find them, find elliptic curve with certain conditions. All right, I'm going to stop here, and then we will continue in the next video with the group law.